All right, let's dive right into this masterclass explainer. We are going to completely level up your skills in BigQuery Graph today, taking you all the way from the absolute basics up to some seriously advanced enterprise architecture. Look, if you've ever wrestled with highly connected data, you already know the traditional methods hit a brick wall pretty fast. So today we're going to fundamentally transform how you view, model, and query the relationships hidden inside your data.
We've got a really packed roadmap for this one. We'll start with why graphs actually matter, break down the property graph model, build your first graph, learn to query it with GQL, explore advanced multi-hop traversals, and wrap up with the unified operational graph.
So, Section 1, why graphs matter, and specifically, why we need to move beyond the traditional SQL join. If you've ever tried to write a query to find a friend of a friend of a friend in standard SQL, you know exactly how painful that is. You just end up with these massive nested join operations. They're a nightmare to write, even harder to read, and when you try to scale them, the performance literally degrades exponentially. But BigQuery Graph completely changes the game here. It uses the new ISO GQL standard, that's graph query language, which is purpose-built from the ground up for traversing relationships. It lets you scale to billions of nodes and edges incredibly efficiently, and the best part is, you don't even have to move any of your existing data. It's an absolute lifesaver for things like calculating the blast radius of a supply chain disruption or modeling really complex network hierarchies.
And just to put into perspective how impactful this is in the real world, companies like Curve are using these exact tools right now for financial fraud detection. As their VP of Data and Machine Learning pointed out, moving to graph-based analytics delivered around £9.1 million in savings. That's huge. They're using it to uncover these deeply hidden connections between seemingly unrelated accounts. Another massive use case for this is Customer 360, where you can track relationships and purchase histories to truly map out the entire customer journey across your ecosystem.
Moving right along to Section 2, the property graph model. Let's get our basics down.
The crucial thing here is just understanding how this specific model works. Basically, we map the real world into entities that we call nodes, so think customers, accounts, or products. Then, the connections between them are called edges, verbs like purchased, owns, or transferred to. We then classify these elements using labels to define their type. And finally, we attach properties, which are really just the data values themselves, like a customer's name or a transaction amount. Oh, and edges can be directed, meaning they show a specific flow like money moving from one account to another. Or they can be undirected for reciprocal relationships.
Now, for those of you who are SQL natives, this translation mental map is going to be your best friend. Just think of a node exactly like a row in a table. An edge? That's essentially an explicitly mapped foreign key or a join between your tables. Your table name becomes your label, and your traditional columns simply become your properties. Once you see it like this, it is such an intuitive way to model reality. Okay, Section 3, building your first graph. Let's look at some DDL magic. To actually build a property graph in BigQuery from your existing tables, and again, I cannot stress this enough, this happens entirely without moving or duplicating any of your data, you use a really simple three-step data definition language process. First, you define your node tables to map rows to entities. Second, you define your edge tables to map rows to those connections. And third, you define element keys. This last step is super important because it explicitly maps the source and destination references so the graph engine knows exactly how all your puzzle pieces connect.
Look at how elegant this syntax actually is. Using just a single create property graph statement, you can instantly layer a graph structure right over top of your relational tables. In this example, we're creating one called FinGraph. We're defining our node tables as account and person and our edge tables as transfers and owns. That is it. One DDL statement and boom, you've got a fully functional graph ready to be explored.
Which brings us to Section 4, Querying with GQL, focusing on the core concepts of match and return.
The best way to think about GQL is that it operates purely on pattern matching. Just look at this query. We use the match keyword to find a specific pattern. Nodes are always in parentheses, like P person. And we can even apply inline filtering right there inside the brackets, kind of like a SQL where clause, by asking for a person with an ID of 1. Edges are represented in square brackets with an arrow, like -owns arrow, pointing over to an account node. Then we just return the specific properties we're looking for. It is incredibly visual. It literally reads almost exactly how you draw it out on a whiteboard.
And here is the absolute best part. For any downstream applications you're running, the output of that match pattern looks just like a standard SQL output. It hands you a clean, two-column table of names and account IDs. You aren't forced to learn or integrate a completely new ecosystem just to consume your results. It just fits right seamlessly into whatever analytics workflows you're already using.
But wait, it gets even better because you have total 100% interoperability here. You can actually combine graph queries and traditional SQL queries together using the graph table operator. You literally get to use the best tool for whatever specific question you have. Plus, you can use the toJSON function to return full multi-hop graph paths, which lets you seamlessly visualize your results directly in BigQuery Studio or your Jupyter notebooks. Now, a quick pro tip for you. If your visualization starts looking like a cluttered mess, just double-check that your toJSON function is returning valid, simplified path structures. That'll ensure clean rendering. Because once you can visualize the graph, you will immediately spot anomalies and clusters that a flat table would completely hide from you.
All right, it's time to level up. Section 5, Advanced Traversals. This is where we get into multi-hop mastery.
So imagine this complex business problem. You need to find the absolute cheapest transfer path between two financial accounts. But this path might bounce across multiple intermediate accounts, let's say across 3 different hops. Now, try to imagine writing a recursive CTE in traditional SQL to calculate aggregations across an unknown number of hops. Actually, scratch that. Don't imagine it. It's terrifying.
But BigQuery handles this beautifully. Take a look at this expert-level GQL syntax. We can use built-in path search prefixes like any cheapest to just let the engine mathematically optimize the route for us. We use quantified path patterns, see that 1,3 right there, to tell the query to look anywhere from 1 to 3 hops deep. And we can even do horizontal aggregation using group variables, employing the let keyword to instantly calculate the sum of the transfer amounts along that exact path. One major best practice here for query performance, always try to use bounded quantifiers like 1,3 instead of unbounded ones, because it guarantees the engine executes your search incredibly fast.
And at the expert level, you aren't just limited to mapping basic columns. You can actually define derived properties and measures directly in your schema definition. You can create custom properties derived from existing columns and define aggregate functions, like a sum or an AVG, right at the node or edge level. This is a game changer because it ensures that aggregations are performed exactly at the correct semantic level for your analysis, which keeps all your downstream queries perfectly clean and highly performant. And this level of advanced traversal is genuinely changing the world right now. BioCortex is leveraging this exact pathway search in BigQuery Graph at a massive scale, going 7 or more hops deep. They are literally using this to identify the precise biological levers that need to be pulled to cure complex human diseases. They're modeling the human metabolism map and emulating life at the speed of compute. I mean, that is the true power of graph analytics at scale.
Finally, let's bring it all together in Section 6, the Unified Operational Graph, combining Spanner and BigQuery.
In any real-world enterprise, you're dealing with both operational workloads and analytical workloads, right? Well, BigQuery Graph is your absolute powerhouse for historical OLAP analysis, perfect for uncovering those massive long-term fraud rings across petabytes of data. But Spanner Graph is its sister engine, built for real-time OLTP operations. Spanner Graph is what can instantly block an active fraudulent transaction at a checkout counter with millisecond latency. The absolute magic here is that both engines share the exact same unified GQL schema language, so there is zero context switching for your engineering teams.
And you can actually bridge them together. By using federated queries with the create external schema statement, you can combine real-time modes that live over in Spanner with historical edges that live in BigQuery, all inside a single query. You can validate a live login attempt against a massive historical web of known bad actors, and you can do it all without moving a single byte of data between the systems.
This whole setup creates the ultimate enterprise feedback loop. Step 1, you detect anomalies instantly on the front lines using Spanner Graph. Step 2, you analyze the deep historical trends and blast radius of those anomalies using BigQuery Graph. Step 3, you use reverse ETL to push those new insights and threat profiles directly back into Spanner for real-time action. It's essentially a continuous, self-improving engine for your entire business.
So we've gone from the very basic concepts of nodes and edges all the way up to unified architectural mastery and complex multi-hop pathways. You now have the power to uncover millions of hidden connections without ever moving your underlying data. So my final question to you is this. Now that the true shape of your data is finally visible, what breakthrough are you going to map out next?